Hello, everybody. These notes are about two things. One is z-scores, and the other is if you imagine z-scores as a transformation of a distribution, how does it squish and shift and reshape the distribution? So z-scores, super useful, and they will continue for the entire rest of the unit. What a z-score is it's a way of taking a measurement and standardizing it so that you can compare it to a distribution, or so that you can compare two measurements in different distributions. So let's kind of see what I mean here. My height in meters, I don't know. You should write your own height in meters here. Let me show you how I'm going to do it. You could, of course, do the calculation yourself, or maybe you already know your height in meters. Here's what I will do. 5 feet 10 inches in meters. And there we go, 1.778 meters. So go ahead and do that for your own height right now. All right, so the question that we're going to answer is that tall? And in order to answer that, it sort of depends on compared to what. So is this tall for a gymnast? Is it tall for a basketball player? So if you look down here, you can see some distributions of heights for Olympic athletes in different sports. So here's Olympic basketball players, cyclists, gymnasts. My height is 1.78 meters, and so just visually on these histograms, 1.78 looks like it's approximately right here. So this is me. So you can see that I am not very tall for a basketball player because I'm considerably shorter than the mean or the median basketball player's height. I'm about average for a cyclist, and it looks like I'm above average for a gymnast. But that's all qualitative. How could we put a number that would tell us how far above or below the average we are? That's what a z-score does. So what a z-score does is it tells you how many standard deviations you are away from the average for a given distribution. So I'm going to do a calculation here. You should do the calculation for your height. The way that you calculate that z-score is you take your observation, you subtract the average for whatever distribution you're looking at, and you divide by the standard deviation. So my z-score compared to gymnasts is going to be 1.78 meters. Go ahead and write m for meters. I'm going to subtract the mean height for gymnasts, which I can find down here. Gymnastics mean is 1.638. And then I'll divide by the standard deviation, which is 0.068. 86. All right. I'll do that calculation in just a second. For basketball, I would have a different z-score because I'm in a different place in the distribution. So again, 1.78 meters is my observed height. I'm going to subtract the average height for basketball players, which is 1.919 meters. Divide that by 0.122 meters. Okay, so go ahead and do that for your own heights and then calculate what the values are. All right, so here's what I've got. My z-score for gymnasts was 1.65, and remember what that means is it's telling me that I'm 1.65 standard deviations above the mean gymnast height. So here's the mean gymnast height, and it's telling me I'm 1.65 standard deviations this way. Here I've got a negative z-score, which means that I'm below the average. So I'm 1.14 standard deviations below the mean of the basketball players. So this means below the mean. So far we have calculated two z-scores, which let us give a quantity, give a number for where is a particular measurement in a distribution. One thing that's helpful is it lets you compare two different values from different distributions. So let's ask this question. Who is taller for their sport? Is it a gymnast who is 1.73 meters? Or is it a basketball player who is 2.04 meters? So in order to answer this question, you would need to look and see how many standard deviations above the mean is a gymnast compared to the mean for gymnasts, and see how many standard deviations is this basketball player above the mean for basketball players. And so you're sort of seeing, compared to their own distributions, who is taller. So go ahead and work out those two z-scores right now. So here I have the gymnast's height minus the mean height of gymnasts divided by the standard deviation of gymnasts, and that gives me 1.07 approximately. Approximately. So slightly more than one standard deviation above the mean for gymnasts. For the basketball player, we have that they are approximately 0.99 standard deviations above their mean. So even though the gymnast is shorter, they are taller for their sport than a basketball player is, because they have more standard deviations from the mean for their sport. So boxed gymnast as taller for their sport. Let's do one more, and this one I won't show you the answer to, but you should complete it, and we'll look at it in class. So I got this data from the internet, but I believe from a reputable source. So in 2021, across the whole United States, the ACT exam, which is a college entrance exam, the ACT scores for US students had a mean score of 20.3 points and a standard deviation of 6 points. SATs, different college entrance exam. Again, in 2021, across the whole US, there was a mean of 1060 points with a standard deviation of 217 points. So you can imagine these two distributions. You could imagine the distribution of, and you won't know the exact shape, but let's imagine that it's sort of unimodal symmetric. So imagine the distribution of ACT scores centered here with a distribution with a spread. Imagine this other one with a center and a spread. So let's pretend I scored 1360 on the SAT. I'm going to be somewhere in that distribution. What I really want to know is, what ACT score would I need to do better? What does it mean to do better here? Doing better on the ACT would mean that I am more standard deviations above the mean for the ACT than I was for the SAT. So this question is really all about z-scores. Give it a try and write in one sentence what your answer is. All right, here we are on the back page. This actually is a lot of stuff to do, so let me focus you on what the purpose is. The purpose here is I want you to practice a few calculator skills. I want to make sure that you remember how to enter data. Can you enter all those into a list? Then I want to show you how to do the same computation to every value in a list. So can you take the entire list 1, add 6 to every single value, and save that into list 2? I'll show you how to do that. Remember how to calculate summary statistics, and then make a histogram out of a list, but I'm going to show you how you can set your own bin widths. So let's go ahead and do all those things. Feel free to skip ahead if you remember how to do this stuff. Otherwise, pause and try it yourself. So step 1, go ahead, hit stat, edit, list 1, and then enter all that data. And now I will do it. Stat, edit, list 1, here we go. All right, now I'm going to show you this piece. How can you do the same calculation for every single value in a list? So what you'll do is you'll hit second list and start with whatever list contains your data. Then you can do whatever operation you want. You can add 6, you could multiply by 2, and then when you're ready to save the results, right down here, the stow button will let you stow the results into second list 2. So hit enter. There's your new list, and if you want to edit it or look at it, you can hit stat, edit, and here's list 2. And you see 3.2 plus 6 is 9.2, and so it's all worked out. All right, now let's, for our original distribution, let's calculate some summary statistics. To try and do that, remember, so like some of these you can read directly from the onevar stats output. Some of these you have to calculate yourself. So pause the video, give it a try, and then I'll do it. All right, I'm going to do it. So we can hit stat, go over to calc, onevar stats. I want to use not list 3, but I'll hit second list to go to list 1. It's not a frequency list, so I'll hit calculate. And here we've got a bunch of values. X bar is going to be the mean, so this is 5.49. The median is down here. It says median is 5.5, so very close. Spread, standard deviation, so let's use this one. It's 1.18, I'll approximate it as. Range is not given here, but you should be able to find range just based on what you know. Here we're going from 3.2 all the way up to 7.4. So you could say 7.4 minus 3.2 gives us 4.2 for the range. And then the interquartile range, let's go back to the one variable stats. So interquartile range is the difference between quartile 3 and quartile 1. So 6.4 minus 4.5 is 1.9. Okay, go ahead and do that same thing right now for your list 2. Your list 2 is the one that's been shifted, and then enter the results here. All right, here's what you should have gotten. We'll interpret these in just a second. Last thing, let's make some histograms. So I'll remind you how to make a histogram, but then I'll show you how you can set your own bin width. So go to second stat plot. We'll turn stat plot 1 on. Oh, hold on. Okay, I just turned my second one off. All right, so stat plot 1, I'll hit enter. If it's not set already, go to histogram. And then here's list 1, that looks good. So ordinarily now you would go to zoom. And then you would, oops. Okay, sorry, I was on second. So ordinarily you would go to zoom. And then you'd go all the way down to 9, or you just hit the number 9 to do zoom stat. And remember what that does is it automatically scales so that your minimum and maximum fit your data, and the bin widths are something nice, and then you can trace if you want. But the problem is I don't want it to look like that. I want it to follow my picture here. I want the bin widths to be 1, going from 0 to 16. So here's how you can do it. Go to window here, and set your x min to be whatever you want the min to be. Here's 0. I'll set x max to be 15. And then x scale, XSCL, is your bin width. So I'll set the bin widths to 1, and then you can hit graph. And so now you see it looks a lot more like mine, and we can trace again. And you see this is the bin from 0 to 1, from 1 to 2, I'm hitting the right arrow, from 2 to 3, and then here from 3 to 4, n is 2. And so you can see that right here. I'm going to do it in pencil. So here from 3 to 4, we've got a bin of height 2. From 4 to 5, we have a bin of height 4. From 5 to 6, we have, from 5 to 6, we have a bin of height 7 right there. So let's go ahead and finish the rest of this histogram. Looks like this. You can probably guess what the histogram of your data that we've added 6 to is going to look like. But just to make sure you can do it, go back to stat plot. Turn on your second plot and have it plot list 2 on these same axes. So you don't have to zoom anymore, you don't have to set the window anymore, it's all set. So go ahead and just turn on stat plot 2 and go to graph. And when you're done, it should look like this. It would be really nice if these were shaded differently, but this was our original distribution, and this is the distribution where we've added 6. All right, so what do we observe? You probably knew all of this before we even started. Adding 6 is a transformation that shifts. So you can see the plus 6 here. So like 3 has shifted up to 10 when we added 6. Uh-oh. So 3 has shifted up to 9 when we've added 6. Ta-da! And let's look over here at our summary statistics. So the measures of center have also added 6, which makes sense because they are positions in the distribution. So if the center was here, now it's 6 higher over here. The measures of spread haven't changed at all, which hopefully makes sense, because if you're just shifting all the values to the right, the difference between the lowest and highest is the same no matter how you've shifted them, because everything's been shifted by the same amount. So you see, like, the range was 4.2 from here to here, same range of 4.2 from here to here. So long story short, adding is a shift, which changes measures of position, but not measures of spread. All right, if you feel like you want extra practice with the calculator, do it all over again. So start with list 1, do list 1, and then times 2, and then stow, and then store it into list 3. So this would be list 1, list 2, list 3. Go ahead and calculate the summary statistics for this data, which has been stretched by a factor of 2, scaled by a factor of 2, and then go ahead and make the 2 histograms. Pause it if you want, otherwise I'll show you what it looks like right now. So here's what it ends up looking like. This is the summary statistics from our original distribution, unchanged, so I just copied from that box to this box. Here are the summary statistics for our scaled distribution. And what I want you to notice is that both the measures of center have doubled and also the measures of spread have doubled. It probably makes sense that the measures of center should double, because what we've done to every single value is we've made it twice as large, which is another way of saying that it is twice as far from 0. So let's look at a couple examples. So here, 3.2 was right there. We double it, and it ends up in this bin that's between 6 and 7, because it's 6.4. This point, which is also in our original first bin, this value 3.9, when we double it, we get 7.8. And so because it's spaced out more, now it ends up in the bin that's right next to it. So everything is stretching in this direction, and so the values that represent the center here are also going to stretch in this direction and end up twice as far away. Measures of spread are also going to double because this minimum value has gone twice the distance, the maximum value has gone twice the distance, and so that distance between them has also doubled. So long story short, again, shifting, measures of spread don't change because everything moves by the same amount. Scaling, you're stretching everything, and so measures of spread also scale. So both measures of center and measures of spread. Something you may have noticed here is that the scaled histogram is only half as tall as this one, roughly. So kind of what's going on? Why is that? Why did scaling at this direction make it be half as tall? Pause for a second and think about it. You probably have a feeling, but see if you can actually form a precise sentence. So hopefully thinking about where these individual data points move will help. So these 2 data points were in the same bin in the original data, but because we scaled them, the scaled data is more spread out, but the bin sizes have remained the same. So the 2 values that used to be in one bin have now spread out to span 2 bins. A different way of saying that is because the data is more spread out and the bin sizes haven't changed, each bin is going to contain roughly half the data. So it's going to be half as tall as the original. Thus, the height of 2 here has become side-by-side heights of 1. So it's stretched this way, but it's become shorter that way. And then if you wanted to read my sentence, I just said, data spread out by a factor of 2, but the bin sizes stayed the same, so each bin has about half as much data in it, and therefore it's half as tall. The only reason I wanted to show you this is because later in the year, we're going to study continuous distributions that look like this. A feature of continuous distributions is that the area under the curve remains 1 at all times. And if you don't know calculus, you don't know how to calculate the area under the curve, but that doesn't matter. A feature that happens when you transform these distributions, it's the same thing here. So if I have a distribution like this, and I scale it by multiplying it by 2, it becomes half as tall in order to preserve that area. So if the width has doubled, the height has to divide in half so that the overall area remains 1. And so I just wanted to flag this as a phenomenon that's going to be important later on, but it sort of comes, the intuition for why this happens comes from thinking about how histograms based on a finite amount of data actually change as the data spreads out. All right, let's bring it home. Let's bring it all together. So This was the equation for calculating z-scores. Imagine you're going to replace every single observation with its z-score. You can think about this now as taking all the x values in a distribution and applying a transformation. I'm subtracting a constant, which is going to transform it, and then I'm dividing by a constant, which is going to transform it. So just to review again, like adding and subtracting a constant is what kind of transformation? If you said a shift or a translation, you are correct. So if I subtract the mean, it takes a whole distribution and it translates it to the left. It shifts it to the left by this amount. And then when I divide by the standard deviation, how does dividing transform a distribution? What kind of transformation is that? Hopefully you said scaling or like stretching or squishing. Stretch, squish. All right, so the mean represents the center of our data. And so like, let's imagine what happens if we subtract the center from all the values. Let's imagine like a hypothetical distribution here, which looks like this. And let's say this is the mean of our distribution. So if I'm going to subtract the mean from every single data point, let's imagine a couple of data points, like this one, this one, this one, this one. So we've got, a bunch of them. So if I have this data point and I subtract the mean, that's like saying this distance minus that distance. So it's going to end up as a negative number. If I have this and I have this distance minus the mean, it's going to end up as a positive number. So another way of thinking about it is subtracting the mean is like saying how far away is this point from the mean? And what that's going to do is it's going to shift your whole distribution by the mean. Think about it this way. What happens when you subtract the mean from the mean? You end up at 0. So this is going to represent a shift all the way to the left so that now your distribution is centered at 0. So that's the first step in thinking about what this equation is doing. This subtracting of the mean shifts the whole distribution so it's centered at 0. And if this is something that you're likely to forget, go ahead and just like annotate, add the description, and that part of the equation. Okay, you can probably guess what's going to happen next. So here's the standard deviation, which represents the spread of the data. So what happens when we take a centered distribution and we divide every value by the standard deviation? So if we take a bunch of data points and we divide them by a number larger than 1, they'll all get smaller towards 0. They'll all scale towards 0, which is like squishing it. So let's imagine our centered distribution at 0 looks like this. And let's pretend that the spread of our distribution has a standard deviation of 2. So it looks like this. This is the standard deviation. If I'm going to divide every single data point here by 2, it's going to squish it that way. So what was 2 is going to end up at 1. What was 4 is going to end up at 2. And so the scaled distribution is going to look something like this. So this is a very conceptual picture. You shouldn't pay too much attention to the scaling. But that's the idea. So this part of the equation shifts your distribution so it's centered at 0. Dividing by the standard deviation is going to squish it so that whatever the standard deviation was becomes 1. And that sort of makes sense, hopefully, because the z-scores tell you how many standard deviations your particular data point was above or below the mean. So here's just an illustrative example. The type of flower called the iris, they've got petals, and they also have other things that are sort of like petals called sepals, and they all have lengths and widths. And so I know there's no color coding here, but you can see several different distributions for the lengths and the widths of petals and sepals for irises. And you can see here, this is bimodal data, this is unimodal, but it's got a small spread. This is unimodal, but it's got a larger spread. If we want to be able to compare all these values to each other, we want to standardize them. So if you take all of these values and you replace them with their z-scores, this is what it looks like. So you can see this distribution here has become this distribution here. Like imagine this shifts to 0 and then gets rescaled by stretching and it becomes that. This tall pointy one shifts to 0, But when it rescales, it gets pulled a little bit wider like that, because it must have been that its standard deviation was smaller than 1. So when we divided it, it ended up stretching out this direction. So I just wanted to show you this as a visual way of thinking about what happens when you replace everything with a z-score. And the idea of normalizing data, which is a good idea when you want to compare different distributions. So normalizing data, again, is like a very, very common first step before you start analyzing it in a lot of different contexts. And we'll learn more about that later in the course. Whew! Thank you for sticking with me. I hope it was worth it.